Okay, so in this video, we want to find a way to find the derivative of exponential and logarithmic functions. We'll start with exponential functions, and we'll realize that the key to figuring out the derivative of any exponential function and any logarithmic function is that one very special exponential function. So let's consider the following graph. This is our x-axis, our y-axis. And consider the graph of y equals 2 to the x and y equals 3 to the x. Both 2 to the 0 and 3 to the 0 are equal to 1, so both functions will pass through the point x equals 0, y equals 1. So this would be, say, y equals 2x. And then if you think of it, for positive values, 3 to the x is bigger than 2 to the x, but for negative values, it's a little smaller. So 3 to the x will start like this. 3 to the 0 is still equal to 1. And then for positive values, 3 to the x is bigger than 2 to the x. So we'll shoot up like this. So we have the two graphs of 2 to the x and 3 to the x. Before we try and differentiate the exponential functions, we'll ask simply about the derivative when x equals 0, y equals 1. What's the slope at this point? So let's look at the derivative of 2 to the x at x equals 0. So the derivative with respect to x of 2 to the x, specifically at the point x equals 0. And here we have to go back to the definition of the derivative. So this is the limit as h approaches 0. The function at x plus h, but x is equal to 0, so we'll have 2 to the 0 plus h, minus f of x, but x is 0, so 2 to the 0, divided by h. So this simplifies. We have the limit as h approaches 0, 2 to the h, minus 2 to the 0 is 1, so minus 1 over h. And then you may ask, well, how could we then figure out this limit? Because as h approaches 0, 2 to the 0 is 1, so we'll have 1 minus 1, 0 over 0 case. The idea is, we don't know how to find this limit yet, so let's find an estimation. Let's take a very small value of h, plug it in, and then get an approximate value. So suppose we take h, say 0.001. Then we'll have an approximate slope. So replace h in the expression here by 0.001. With the help of your calculator, you will find approximately 0.693. So roughly speaking, this is only an estimate of the derivative of 2 to the x at the point 0. So roughly speaking, the slope of y equals 2 to the x at x equals 1 will be a little smaller than 1, roughly 0.639. We may ask now, what about the slope of 3 to the x at x equals 0? And we can see that the graph of 3 to the x at 0 is a little steeper than the one for 2 to the x. So we expect the slope of 3 to the x at 0 to be bigger than 0.639. Well, let's see what we have then. So the derivative of 3 to the x, specifically at x equals 0, well, this would be the same as for 2, except we change 2 for 3. So the limit as h approaches 0, 3 to the 0 plus h, minus 3 to the 0 over h. Again, this simplifies as the limit as h approaches 0 of 3 to the h minus 1 over h. So once again, we have a 0 over 0 case. So we'll take the same value of h, 0.001, And then we'll plug it in. We won't get the exact slope at 0, but we'll have an approximate slope. So using your calculator, 3 exponent 0.001 minus 1 divided by 0.001 gives you approximately 1.099. You can round up to 1.1. So here's what's interesting. If you go back to the graph of 2 to the x and 3 to the x, you can see that at 0 specifically, the slope of 3 to the x is bigger than the slope of 2 to the x. The slope of 2 to the x at 0 is roughly 0.69, and the slope of 3 to the x at x equals 0 is roughly 1.1. And then the question is, does there exist a number between 2 and 3 where the slope at 0 is exactly 1? If you think of it, if you go back to the graph, as you would increase 2, the slope at 0 would increase as well. And as you reach 3, the slope has reached a number that is approximately 1.1. So there has to be a point as you slowly increase 2. You can think of 2, 2.1, 2.2. And as you slowly increase 2, the graph will become a little steeper and steeper at x equals 0. And so at some point between 2 and 3, the slope has to be exactly equal to 1. And this is now our conclusion. And we'll see from there what that implies. So there must exist a number and we'll call this number e. So there must exist a number, say e, between 2 and 3, such that the slope at 0 is exactly equal to 1. So between 6, at 2, you have 2 to the x has a slope of roughly 0.69 at x equals 0. As you gradually increase 2 up to 3, there will be a point when you'll have exactly a slope of 1, and that's the number e, such that the derivative, the slope of e to the x at 0 will be exactly equal to 1. And now you may ask, well, what is this number? Right now, I won't show you how to evaluate it, but I can at least give you an estimate. In our next video, we'll see how we can evaluate this function, or at least the value of e. So if you look at your calculator, you'll have the function exp, and that is exactly the exponential base e. And this will be exp of 1, which is, if you want, e to the 1. And this will be approximately 2.71828 ... Now why ... This number happens to be an irrational number. So it has an infinite decimal expansion, and there is no repeating pattern. But at this number, so if you were to draw it, y equals e to the x, with this choice of base, which is approximately 2.71828, the slope at 0 will be exactly 1. Another question is, you say, okay, we have that the derivative of e to the x with this choice of e, 2.71828, is exactly equal to 1. Well, what about the derivative of this function at other values of x? Let's just rewrite what this gives us as a limit. Right? If you rewrite this the limit, you'll have the limit as h approaches 0 of e to the h minus 1 over h, and this limit is the derivative of e to the x, specifically at x equals 0, And we chose e to be so that the derivative at 0 is exactly equal to 1. And now let's see with the help of this derivative, not derivative but limit, if we can find the derivative of e to the x at any other given value of x other than just 0. And what we'll find is actually quite interesting. So let's recall what we have right now. We have this bizarre number right now that is irrational. That is approximately 2.71828 ... And we know that the way we chose it is so that the function y equals e to the x has a slope of exactly 1 at x equals 0. Hence the limit, as x approaches 0 of e to the h minus 1 over h is exactly equal to 1. And with this limit, we can now find the derivative of this function for any value of x. And let's see what comes out. And what will come out, hopefully, will surprise you. So we ask, what's the derivative of the exponential function base e to the x, at any given x? So here we have to go back to our definition. We let h approach 0. We have the function at x plus h minus the function at x over h. And now the question is, how do we go from this limit to the answer using the fact that we know this limit is equal to 1? Well, let's just rewrite this term here, because we know e to the x plus h is just e to the x times e to the h. Right? If you multiply the same base, you add the exponents. Let's do that here. So the limit as h goes to 0, this is e to the x times e to the h minus e to the x over h. Now both terms on top are multiples of e to the x, so we can factor it. So we have e to the x times, we're left with e to the h minus 1 over h. But if you go back to how we defined e was the number between 2 and 3 with this property. So as h shrinks to 0, e to the h minus 1 over h approaches 1. And this is what we have right here. This will approach 1. And therefore, we'll, in the limit, end up with e to the x. As h approaches 0, there is no h here. So this will stay e to the x times this expression which approaches 1. So we'll be left with e to the x times 1, which is e to the x. And look at that. The derivative of the exponential function base e of e to the x at any value of x is equal to itself. Nothing has happened. So the function is its own derivative. And now we have it. The derivative of the exponential function base e is equal to itself, where e is this irrational number that is approximately 2.71828. And I claim that now with the one derivative for this very special case of a base, where e is 2.71828 approximately, we can use this to differentiate every other exponential function and every other logarithmic function. The last thing we need is the derivative of the inverse function of e to the x. So if you remember, the inverse function of an exponential is the logarithmic function with the same base. So the logarithmic function, base e, will be the inverse function of e to the x. So this is, by definition of what a logarithm is the inverse. The inverse function of y equals e to the x. So y equals log base e of x is the inverse function of y equals e to the x. And because e is such a special number, we actually give this a new name. We will never write log base e of x as we will see in our next videos, the base e is so important that we will give its logarithmic function a special name. We will simply write this as ln of x, and we call this the ln of x. All it is the special logarithmic function base e. And so now you ask, well, okay, what is the relationship, therefore, between ln of x and e to the x? Well, it is the inverse function, and the inverse has a property of canceling the function with respect to composition of functions. So if you would say take the ln of e to the x, so you first exponentiate x, then take the ln base e of this, all you will get is x. And you can also ask, what if I take the exponential of the ln of x? Same thing, you get back x. And that is the property of an inverse function. It cancels the other function with respect to composition. So think of it this way. When you write ln of e to the x, the ln is by definition log base e of x, and it cancels e by composition, so ln cancels e, and all you're left with is the argument x. Same thing if you compose in the opposite order. If you do e to the ln of x, well, because ln is the inverse of e is also the inverse of x, of ln. Ln is the inverse of e, so e is the inverse of ln. So if you take e to the ln of x, e will cancel ln, and you get back once again the argument x. And now with this relationship, let's see how we can find the derivative of ln of x using implicit differentiation. And as soon as we have the derivative of ln, in our next video, we will find the derivative of every other exponential function and every other logarithmic function. So recall what we have right now. We have just derived for this number, which is approximately 2.71828, that the derivative of this function, as amazing as this sounds, is just equal to itself. And now we want to find the derivative of the inverse function, ln of x. And we know that ln is the inverse of e, so e to the ln of x equals x, and the ln of e to the x is also equal to x. With this relationship, we will be able to find the derivative of ln of x from the derivative of e to the x. So let's start with our function, y equals ln of x. What we want is the derivative of ln of x, hence we want dy over dx. Well, the problem is that we don't really know how to differentiate ln of x. That's the question we're trying to find. So the idea is we can get rid of ln if we exponentiate base e. So if y equals ln of x, then e to the y is equal to e to the ln of x, right? Y is equal to ln of x, so we can replace y in the exponent by ln of x. But e is the inverse function of ln, so e will cancel ln, and all we're left with is x. And now we have this new relationship, e to the y is equal to x. And now we're good to go. We've got rid of the ln function, but we know y is a function of x. Y is ln of x, and now we can use implicit differentiation. We have an equation involving y, which we know is a function of x, and so this function of x equals this function of x, hence they must have the same derivative. So if we differentiate the left-hand side with respect to x, which is e to the y, this will be the same as the derivative of the right-hand side with respect to x. So what do we get now? Well, let's start with the easy differentiation. The derivative of x with respect to x, that's just equal to 1. And now let's be careful here about our e to the y. When we ask, what is the outside function? Because we have a composition. We take the exponential of y. And it may look like y is the outside function, but you have to be careful, right? This is the exponential of y. So think of it this way. If you want to compute this, you have to first plug in the y value, then taking the exponential. So the exponential is the outside function. So by the chain rule, we differentiate the outside function, which is the exponential, and the derivative of e to the x is just itself. So the derivative of e is just e. E of what? Well, e of what's left over, which is y. But there's still a y left over here. And by the chain rule, we have to multiply what we have so far by the derivative of what's left over. What's left over is y, so we have dy over dx. And now we're done with the derivative of e to the y with respect to x. It's just e to the y times dy over dx. But now we can simplify a little more. E to the y, we know is equal to x. So what we have is actually quite simple now. E to the y is equal to x. So we have simply x times dy over dx is equal to 1. Divide both sides by x, and so the derivative of y with respect to x is just 1 over x. But if you remember y, that was just ln of x. And so we have it. The derivative with respect to x of the function y, which we called ln of x, so the derivative of ln of x is remarkably simple. It's 1 over x. And recall that the derivative of the inverse function e to the x is also remarkably simple. It's just itself. And now with these two derivatives, in our next video, we will show we can differentiate any other exponential function if we change the base, and any other logarithmic function if we also change the base from e to any other base. Finally, let's just graph the function e to the x and ln of x. So if you remember, think of e as roughly 3. It's 2.71828 dot dot dot. So think of e as roughly 3. So 3 to the x would look like this. So y equals e to the x would look pretty much the same. And now if you remember, the definition of ln is it is the logarithmic function base e, hence the inverse function of e to the x. And to graph the inverse function of a function, you have to look at the line y equals x, and then if you reflect the function about this line y equals x, you will have the graph of the inverse function, which will look something like this. And that's the graph of ln of x. And because e to the 0 is 1, ln of 1 is equal to 0. So you have here the graph of e to the x and the graph of the inverse ln of x.